Today we're going to talk about how to use double integrals to find the surface area of the part of this function z equals xy that lies inside x squared plus y squared equals 1. So as a reminder here, I have the formula for surface area using a double integral. Notice that the only thing real complicated about it is just that we have to take partial derivatives of z with respect to both x and y. So we can go ahead and do that now. Because we're finding surface area of this function z equals xy, we want to take partial derivatives of this one. We're going to use this equation, x squared plus y squared equals 1, to find the bounds, our limits of integration, because this equation here is bounded by this one. We're looking for surface area of this that lies inside this. So let's go ahead and take partial derivatives of our function z with respect to x and with respect to y. When we do that, remember, if we take the partial derivative with respect to x, we treat x as the variable and y as the constant, which means that in this case, y is just a constant coefficient on this first degree x variable here, so the partial derivative with respect to x will just be y. The partial derivative of z with respect to y will just be the opposite scenario, and we'll end up here with x. Now we can plug both of those into our double integral here in place of these partial derivatives here. Now all we need is upper and lower limits of integration for both x and y. Now because we just have this circle here, right, x squared plus y squared equals 1, the graph of that is just the unit circle where the radius here is 1 out a distance of 1 from the origin. So here's our graph. We can treat this as a type 1 region. And if we're treating it as a type 1 region, we can go ahead and integrate first with respect to y and then with respect to x. So our surface area integral here, double integral, will say the surface area is going to be equal to, I'll leave placeholders for our limits of integration, and we'll go ahead and write everything else in. So we have 1 plus the partial derivative with respect to x, which we know is just y. We're going to square that, and we're going to get y squared. Then the partial derivative of z with respect to y we know is x. When we square it, we get x squared. And then dA here, we're going to replace dA with dy dx, and the reason is because we can treat this as a type 1 region. We can draw vertical cross sections here that would allow us to find the area of this region here. So we'll integrate first with respect to y and then with respect to x because we can treat it as type 1. That means that our inner integral here is going to have limits of integration with respect to y because the dy is on the inside. Since dx is on the outside, our outer integral will have limits of integration with respect to x. So because dy is on the inside, our limits of integration with respect to y need to be functions for y in terms of x. And the way that we'll do that is by solving our bounding equation here for y in terms of x. When we do that, we'll subtract x squared from both sides and we'll be left with y squared is equal to 1 minus x squared. When we take the square root of both sides, we get y is equal to positive or negative square root of 1 minus x squared. Therefore, we know that our upper and lower limits of integration for y are these two values here. So we can say that y will be greater than or equal to negative square root of 1 minus x squared and less than or equal to the square root of positive square root of 1 minus x squared. Those are therefore going to be our upper and lower limits of integration with respect to y. So we can say negative 1 minus x squared and positive square root of 1 minus x squared. Now, because we're integrating first with respect to y, we said that our limits of integration with respect to y need to be functions of y in terms of x. Because we're integrating with respect to x second, and dx here is on the outside, our limits of integration with respect to x can just be constants. Well, as we can see from our circle here, the leftmost value that x can possibly attain is right here, and that's at x equals negative 1. The rightmost value that x can possibly attain is right here at x equals 1, so negative 1 to positive 1 are our limits of integration for x. Now we've got our integral set up and we just need to solve it. The easiest way to solve this integral, especially since we're dealing with a circle here, is to change the integral from Cartesian coordinates to polar coordinates. We just want to change everything in here to polar notation in terms of r and theta. So remember the equations: r squared equals x squared plus y squared, x equals cosine theta, and y equals sine theta. Those three equations which we can use to convert from Cartesian coordinates to polar coordinates. Well, if we want to convert this integral, we can deal with limits of integration in a second. Right now we'll leave placeholders for those. But remember that we have r squared equals x squared plus y squared. So inside of our integral, we can go ahead and substitute r squared for x squared plus y squared, and you can start to see why it's very convenient for us to change to polar. So we get 1 plus r squared, putting r squared in place of this y squared plus x squared here. Then whenever we change to polar, dy dx always gets replaced with r dr d theta in that order. If you have dy and then dx, we get r dr d theta. Now because here we're integrating first with respect to r, because dr is on the inside, our inside integral here is going to need to have limits of integration with respect to r. Well, if we look here at our circle, our limits of integration with respect to r, the lowest value that r can attain, if we are treating this now as a polar coordinate plane here, the lowest value r can attain is 0, which is right here at the origin, right? So 0 is our lower limit of integration. Our upper limit of integration is the largest radius that is attained anywhere inside this circle. So how far out does r go in any direction? Well, in every direction that I go, the radius is 1. So the largest value that r ever attains, the largest distance away from the origin, is just 1. Now, these are my limits of integration here with respect to r. I'm also going to need limits of integration here with respect to theta. Now for theta, remember theta is the angle. We want to talk about the smallest and largest angles that bound this circle. Well, since it's the entire circle and we want the whole area, obviously the smallest angle is just the angle 0 here along this axis, and then we can go around the entire circle all the way back to an angle of 2 pi because we want to get the full circle here. If we were just asked for the semicircle here above, let's say the x-axis, then we would want upper and lower limits of integration of 0 to pi. But because we want the entire circle here, we're going to say 0 to 2 pi. Now, as you can see, changing from Cartesian to polar coordinates makes our integral look a lot simpler, so it's going to be easier to solve. The way that we're going to solve it is with u substitution. We'll set u equal to 1 plus r squared. We'll take the derivative of u and get du. The derivative of 1 plus r squared will just be 2r, and we add dr there as always. We can solve this for dr by dividing both sides by 2r, and we see that dr is equal to du over 2r. Now if we go ahead and make substitutions back into our integral, we'll get 0 to 2 pi of 0 to 1 of the square root of u times r, we can't forget this r here, and then for dr we got du over 2r, and then we have d theta. Now notice our r variables here are going to cancel, and what we're left with is the integral from 0 to 2 pi of the integral from 0 to 1. This 2 here in the denominator can just get brought out in front as 1/2, and then square root of u is the same as u to the 1/2 power du d theta. Now when we integrate here with respect to u, we'll get 0 to 2 pi. We'll add 1 to the exponent to get u to the 3/2. We'll divide the coefficient by our new exponent, so 1/2 divided by 3/2 is the same as 1/2 times 2/3, so we're just going to end up with 1/3 out in front here, and then we're going to be evaluating that on 0 to 1 after we back substitute for u. So we'll have d theta. We'll back substitute for u. Remember we said u is equal to 1 plus r squared, so 0 to 2 pi of 1/3 times 1 plus r squared raised to the 3/2 power on the interval 0 to 1, and of course d theta. Now if we plug in our upper limit of integration 1 to our 1/3 times 1 plus r squared raised to the 3/2, we'll get 1 plus 1 inside here. 1 squared is just 1, so we get 1 plus 1, which is 2. 2 raised to the 3/2 is going to be square root of 8, because 2 to the 3rd is 8, and then 8 to the 1/2, taking into account the 2 here in our denominator, 8 to the 1/2 is square root of 8. Square root of 8 times 1/3 is just going to be root 8 over 3 when we plug in 1. When we plug in 0, we'll get 0 squared here is 0, 1 plus 0 is 1. 1 raised to the 3/2 is still just 1, times 1/3 is just 1/3, so we get minus 1/3, and then d theta. Now if we integrate this with respect to theta, we'll of course get root 8 over 3 times theta minus 1/3 times theta, evaluated on the interval 0 to 2 pi. If I plug in 2 pi first, I'll get root 8 over 3 times 2 pi minus 2 pi over 3 when I plug 2 pi into 1/3 times theta. Then I'm going to subtract whatever I get when I plug in my lower limit of integration, but of course plugging in 0 will just give me 0 and 0. So I'm just left with this here. So now when I simplify and say 2 pi square root of 8 minus 2 pi all over 3, if I factor out a 2 pi over 3, what I'll get is 2 pi over 3 times root 8 minus 1. I can go ahead and simplify the root 8 a little bit further. Remember that root 8 is the same as the square root of 4 times 2, so I can take the square root of 2, pull it out in front, and say 2 root 2, which means my final answer here will be 2 pi over 3 times 2 root 2 minus 1. And that's it. This is the surface area of this function z equals xy that lies inside the circle x squared plus y squared equals 1. So I hope you found that video helpful. If you did, like this video down below and subscribe to be notified of future videos.